Alright, let's take a look at example number, well, it says 4.3. I think it's all the other typos. Gosh, this is chapter 5. At least, sorry, it's our 5th chapter, so we can call it chapter 5. These all say 4.3, 4.4, and so forth. Oh, whatever the one, whatever. The one that says example 4.3, that's the one we're going to do. We've got a person skateboarding with a constant speed of 1.3 meters per second and releases the ball from a certain height, so it falls down vertically. So just write that right now. Okay. So the person, and if this person is like most skateboarders I know, they skate horizontally. There's our skateboarder right there. Okay, so we have initial velocity in the x direction. Okay, that the skateboard is moving, and that is 1.3 meters per second. 1.3, all right, meters per second. But they dropped the basketball downwards, and last time I saw something dropped, it fell in the y direction. So we got a basketball right here. It's a very large basketball falling downwards. Now, when you drop something, what's the initial velocity? The initial velocity in the y direction is 0. Okay, so initial velocity y is 0 meters per second because you're dropping it from rest. And this is going to be what we start our problem on. The fact that it has a horizontal initial velocity, but no initial vertical velocity. All right, well, let's. In fact, I'm going to move this y value around here a little bit. I'm going to put it. I'm going to put it further down, right here. V initial in the y direction equals 0 meters per second. Sorry, that's a little sloppy right there. What else are we told about this? We're told that xo, or you might say xi, is equal to 0. That means that the initial x position we call 0 meters. Wherever it starts in the x direction, we call that 0. All right, so it doesn't start with any position. It starts at the origin, you might say, in the x direction. And our height, okay, so our y O, or our yi, you might say, the initial starting position of the ball in the y direction, is 1.25 meters. 1.25 meters. Okay, so we have a starting x position and a starting y position. xo or xi, again, those are the same thing, and yi right here. Well, what else can we determine from this? Well, we have 3 parts that we're given times of, and we're asked to determine what the final x position is. xf, that's what we don't know. Sorry, this is so jumpy, that's so sloppy there. yf, you might say, the final y position. We want to find that out. We want to find those final positions for 2 different times. For A, it's for t equals 0.250 seconds. In fact, I'll just write this up at the top here. For part A, time equals 0.250 seconds. For part B, time equals 0.5 seconds. And part C, well, we'll do that a little bit later. And we want to find the final x and the final y for each of those 2 times. What else can we write down? What about acceleration? Okay, we have an initial velocity in each direction. What about an acceleration in the x direction? ax, what would that be? That would be 0, right? Because if it's a projectile, this falling basketball, it doesn't have any acceleration in the x direction. It's moving forward, but when it's let go, it is simply under the influence of gravity. So nothing is moving it in the horizontal direction at all. On the other hand, A in the y direction, yeah, we definitely have that. That's negative 9.81. meters per second squared. Oops, I forgot my squared up here, didn't I? There we go. So we have an a in the x direction, well, which is 0, but we definitely have an a in the y direction right here. Anything else we know? I think that should be good to get us started. Okay, for a, we want to know displacement. That is x final equals what? Okay, well, we know an x initial, and we know the initial velocity in the x direction, so we should be able to solve for x final. You recall that velocity, equals the difference in displacement, x final minus x initial over time, right? The velocity is displacement over time. So we should definitely be able to solve for our final x right here. So I'm going to, let's see, I'm going to multiply the t, bring that up next to the vix, and then I'm going to subtract the xi. So v initial in the x direction times t plus xi, right? We're gonna add that to both sides. X initial equals x final. All right, let's rewrite this over here. X final equals initial velocity in the x direction. Okay, 1.3 meters per second times, what's our time t? We're told up here, right? 0.250 seconds plus our x initial. What's our initial x position? Ah, that's 0. Okay, well, I'll write that in just for the heck of it, but that's not going to do anything. Okay? So now we should be able to solve for our final x position after 0.250 seconds. X final, oops, there we go. X final is what? X final should be 0.325 meters. 25, looks like a 6, but that should be that's just terrible. It's just, there we go. 0.325 meters, or you might say 0.33 meters if you round it. Okay? That's that in the x direction. Now how about the y direction? xy, I'm sorry, yf I mean. Y final, you might say, in the y direction is what? Well, we've got more to work with here because we have an acceleration and we have an initial position. So let's try, let's see, well, we have a displacement, let's see, if you guys recall that change in any displacement, like delta x or delta y, is initial velocity times time plus 1/2. Man, this is getting jumpier and jumpier. Sorry for that bad handwriting. 1/2 acceleration times time squared, right? And this delta y is the same thing as y final minus y initial, so I might as well go ahead and write that out. Y final minus y initial equals initial velocity, I should say, in the y direction. VIY right there times time. And it's a little crowded, but it doesn't really matter. Why? Because the initial velocity in the y direction is 0. So I'm going to just take that and cross that out entirely. That all becomes 0. And that's going to become of no consequence. But we still do have the plus 1/2 AT squared. All right, let's move our yi over there, and then we can plug and get our answer for y final. Y final equals, let's add the yi to both sides. So yi plus 1/2 AT squared. What's our y initial? Okay, that's 1.25 meters plus 1/2. You can put 0.5 if you want. Plus 1/2 times acceleration, which is in the y direction, that's negative 9.81 meters per second squared, times time squared, right? And again, in this case, time is 0.250 seconds. 0.250 seconds squared. That will give us an answer for y final. And that's what? Our y final should be 0.94 meters. 0.94 meters. So it's dropped a little less than a meter in 1/4 of a second. But of course it hasn't hit the ground because it started higher than that. So let's see here. I'm just gonna go ahead with part B again. With part B. Well, part B, the only thing that's different is the time. Part A, we're given this time right here, which is 0.250 seconds. Part B, it's asking for exactly the same thing. It's asking for the position of XF and YF after a certain amount of time, but the certain amount of time has changed. So that's the new time right there. So we should definitely be able to handle that. In fact, we could plug in exactly the same equations. So let's do that. I'm going to write it down here so it's right next to everything else. In B, x final is, what's that? The the initial x velocity, right? 1.3 times the time. In this case, it's 0.5 seconds. And x final in part B, that's 0.65 meters. Okay, that's part B. Whoops, that was a bad box right there. Okay, and we can do the same thing for our y. In fact, let's just use the exact same equation here. I'm gonna shift it up here a little bit. YF equals initial y position plus 1/2 at squared. Remember, because the velocity, the y velocity dropped out because there was no initial y velocity. So our initial y position is 1.25 meters. I'm going to leave the units out for now. Plus 1/2 times acceleration, which is negative 9.81, times time, which is now 1/2 a second, squared. 0.500 squared. Exact same equation, just different time. So what's our y final in part B? Well, just punch it in. It should be 0.024 meters. 24 meters. Which is pretty low to the ground. Which makes sense because the longer it's been falling, the more likely it is to be close to the ground. So that's our final y position after 1/2 second. So all we did was did the exact same equations over here, but we just put in new time values for them.